Welcome back to the Deep Dive. Today we are tackling, well, maybe the biggest question in all of physics. It's a question that the great John Archibald Wheeler spent 60 years of his life circling. What is reality actually made of?
Right. I mean, is it particles? Is it energy? Or is it something much, much weirder, like pure information?
Wheeler was one of the true giants. He was there for the dawn of the nuclear age. He's the guy who made the term black hole famous, and he spent his later years trying to boil everything down to just 4 letters he wrote on his chalkboard at Princeton.
To Puget from bit.
Exactly. It's from bit. The idea that physical reality, the it, somehow emerges from simple binary answers, from information.
And for our deep dive today, we're going to take that idea and run with it. We're plugging Wheeler's entire legacy, his ideas on gravity, black holes, all that quantum weirdness, into a really radical framework called motion theory, or MT for short.
So the core question for us is, if Wheeler was right, if information really is the key, what does that universe look like if the only thing that exists, fundamentally, is structured motion?
MT basically claims to be the operating manual Wheeler was always searching for. It's a huge claim.
It is a huge claim. So before we get into the black holes and the quantum mind benders, we really need to lay out the basic language of motion theory, because it asks you to, completely flip your perspective.
It really does. So let's start with the absolute core principle. In this framework, motion isn't something that objects do.
Okay.
Motion is what objects are. The entire universe is just this vast interconnected network of motion. Nothing else.
Right. So if everything is just motion, what is an object? What is this table?
An object, whether it's an electron or a star, is just a long-lived, stable pattern of structured motion. It's a self-reinforcing loop. If that pattern breaks down, the object is gone, but the motion just rejoins the wider network.
Okay, I can sort of get my head around that for structure.
Yeah.
But what about time? Time feels like this unstoppable river flowing in one direction.
In MT, time is emergent. It's simply how we count stable, repeating cycles of motion. The tick of a clock, the vibration of a cesium atom, they're just reliable patterns. Where you have more stable cycles, you have a more stable sense of time.
So time is counting motion. What about space? Is it just the empty box that all this motion happens in?
Nope. Space is also a derived property. It's all about gradients in that motion network. Think of it like resistance. Space just describes where motion can flow easily versus where it, meets some friction.
And that leads directly to mass and gravity, I'm guessing.
Directly. Mass is simply the resistance to retuning a motion pattern. How hard is it to change its frequency or direction? And gravity. Gravity is what happens when motion patterns converge toward regions where they can synchronize more densely. Motion likes to sync up.
Okay, that's a whole new vocabulary. And it gives us a really powerful lens to look at Wheeler's first huge intellectual pivot.
Yeah.
He started as a nuclear physicist, right? Working on the Manhattan Project, dealing with very real, tangible stuff.
Very tangible stuff. But in the 1950s, he just walked away from particle physics and dove headfirst into something he called geometrodynamics. He wanted to get rid of stuff altogether.
That's where his famous line comes from, isn't it?
It is the most elegant summary of general relativity ever. Mass tells spacetime how to curve. Spacetime tells mass how to move. For Wheeler, the universe wasn't made of little bits of matter floating in space. It was made of pure, curved geometry.
And motion theory would say he was almost there. He was so close. He saw that geometry was key, but he missed one step.
Exactly. The geometry itself is just an expression of the underlying motion. What we call curved spacetime is, in MT, just the global pattern of how all that motion routes all the other motion.
So a big star isn't bending a geometric sheet. It's this huge, stable pattern of motion that creates a massive, what did you call it, a motion gradient?
A strong motion gradient. It changes the resistance of the local network, so other motion, like light or a planet, has its path bent because that's now the easiest route to take. Gravity is just the path of least resistance in the motion network.
And Wheeler had a prototype for this idea, didn't he? The geon.
He did. Geons were these amazing thought experiments. They were lumps of pure electromagnetic energy, just light, so incredibly dense that their own gravity would hold them together. They would look and act just like a particle of matter.
But there's no stuff inside. Just pure energy, pure motion, creating its own stable structure.
And that's the key. MT sees geons as perfect examples of self-trapped motion patterns. They are these little zones of maximum synchronization density. Wheeler showed that structure could mimic substance, and that's a crucial step toward saying it's all just structured motion.
So from geons, it's not a huge leap to his most famous contribution, the black hole.
Hmm.
He popularized the term, and he understood them as the absolute extreme of gravity.
The ultimate endpoint of gravitational collapse. And in the MT framework, a black hole is the ultimate convergence of motion. The synchronization density gets so extreme that it forms an event horizon.
And that horizon isn't a physical surface you could touch, right?
Not at all. It's a boundary in the motion network itself. It's the point where all available paths that lead outward simply cease to exist. All the motion patterns inside are trapped, irreversibly.
Which brought Wheeler to another one of his famous and, frankly, frustrating slogans, black holes have no hair.
Meaning you can only know three things about it from the outside. Its mass, its charge, and its spin. Everything else about the star that collapsed to form it, its chemistry, its magnetic fields, all that incredibly specific information seems to be just gone.
And that's the heart of the information paradox that obsessed him. How can nature just delete information? We know from Bekenstein and Hawking that the entropy, the hidden information, scales with the area of the horizon, not its volume.
Which is incredibly weird. Why the surface area?
So if MT is right and structures everything, what is that area measuring?
MT proposes that the area is proportional to the total number of coherent phase-locked motion patterns that can exist on that surface. We call this coherent entropy, or SOCO. The bigger the area, the more ordered information it can store.
But the paradox remains. A star falls in, its information vanishes, and the black hole eventually evaporates away as perfectly random thermal Hawking radiation. Wheeler hated the idea that information could be permanently lost.
He really struggled with it, but MT offers a very specific answer here. The information isn't destroyed. It is fundamentally retimed and scrambled.
Retimed and scrambled. What does that mean?
The event horizon acts like an ultra-dense motion synchronizer. It takes all the incoming motion patterns and locks them into new, deeply correlated but hidden configurations. It's like taking a library of books, shredding them all, and then weaving the fibers into a single, vast, intricate tapestry. The information is all still there, just in a completely different, scrambled format.
Okay, so the information is preserved. But if it's scrambled into some unified tapestry, how could we ever possibly verify that? How is that not just a story?
Because this framework makes a testable prediction. If the scrambling is efficient but not perfect, if the underlying information is preserved in the structure, we should be able to see tiny echoes. Specifically, MT predicts subtle phase echoes in the gravitational waves we see when black holes merge. When they ring down after the collision, the signal shouldn't be perfectly smooth. It should have these tiny 1/n corrections in the phases of the waves.
Wait, so the ringing isn't just a simple tone dying out. It contains these little whispers, these echoes of the internal structure on the horizon.
Exactly. They aren't classical bounces off a surface. They're echoes of the coherent motion structure leaking through the thermal noise. If our gravitational-wave observatories, like LIGO, can ever measure those specific phase echoes, it would be powerful evidence that the horizon is a retiming device, not an information shredder. It turns Wheeler's philosophical problem into something we can actually look for.
That's incredible. Okay, so from gravity and black holes, Wheeler also pushed deep into the quantum world. And this is where we get his most famous thought experiment, the delayed choice experiment. This is the one that really makes you question what reality is.
Oh, it's a total mind bender. You set up a simple interferometer. A single photon comes in and hits a beam splitter, so it can now take one of two paths to a detector.
Path A or path B? Simple enough.
Here's the twist. The experimenter waits until the photon is already past that first choice point. Then, at the very last nanosecond, they decide whether or not to insert a second beam splitter right before the detectors.
And if they put the second one in, they see a wave-like interference pattern, as if the photon took both paths at once.
Correct. But if they leave it out, they can tell which path the photon took. It behaves like a particle. The insane part is that the choice made now seems to determine whether the photon was a wave or a particle back then.
It feels like the present is reaching back and changing the past. Wheeler called it the participatory universe, right?
He did. The idea that the observer's choice finalizes reality. But motion theory offers an explanation that, avoids the need for time travel.
Okay, I'm listening. If the photon isn't a little ball, what is it in MT?
It's a bundle of possible motion patterns that are all evolving in parallel. The entire system, the photon, the splitters, the detectors, is one global, synchronized motion pattern that contains multiple potential histories.
So before the final measurement, both the wave history and the particle history are sort of on the table.
Exactly. They're both potential states of the global pattern. When the observer makes that final choice, flipping the beam splitter in or out, They're not changing the past. They're changing the constraints on the motion network in the present.
Ah, so the observer is a complex motion pattern that can deliberately introduce a new constraint.
Right. And when that happens, the entire global motion pattern instantaneously retunes. It settles into the one history that is consistent with that final constraint. Nothing in the past literally changes. What changes is how reality commits to one specific structured motion out of the whole family of possibilities.
That reframes participation completely. We're not mystical observers creating reality. We are physical motion patterns, capable of actively retuning other motion patterns. The past wasn't set in stone until the final interaction locked it in.
It's a mechanistic explanation for why reality seems so fuzzy and potential-filled until you actually look at it.
This all brings us back to IT from bit. Wheeler said reality comes from binary questions. MT agrees, but it says that a bit can't just be an abstract yes or no. It has to be physical.
Yes, absolutely. In MT, a bit is a physical thing.
Yeah.
It's a pair of distinguishable motion states that exist under some set of constraints. And a logical operation, like in a computer, is just a controlled retuning of those synchronization patterns.
But if the universe is a computer, there has to be some kind of bookkeeping. There has to be a cost. Wheeler gave us the slogan, but what are the rules of this information economy?
This is where MT gets really concrete. We have to introduce what we call the split entropy or the coherence ledger. Usually we think of entropy as thermal random motion, disordered heat, let's call that CERNet. But MT says there's another kind, CELHOD, which is ordered, coherent, phase-locked motion. This is the stuff that builds stable structures, the stuff that lets you compute. It's useful information.
And you can't get one without the other. There's a trade-off.
There is always a price. This is the crucial ledger rule. Every single time you sharpen a bit or make a measurement or increase the local order, you have to pay for it. You have to dump heat, increasing the thermal entropy somewhere else in the system.
So if I'm building a quantum computer, which depends on these incredibly ordered coherent qubits, that order has a thermodynamic cost. There's a heat bill I have to pay.
Precisely. And this gives us a concrete, measurable rule. The change in thermal entropy is approximately equal to minus some constant times the change in coherence. This is the price tag on information. It's the operational upgrade to IT from bit. It tells you the exact cost of asking one of Wheeler's binary questions.
Which means it's falsifiable. We can go into a lab right now with qubit arrays or advanced NMR systems and track both the coherence and the heat at the same time. If we ever find a system that creates order for free,
then motion theory is wrong. It's the ultimate check. Wheeler wanted equations, not just insights. This ledger rule is one of those concrete, testable equations.
Okay, one last Wheeler concept, quantum foam. His idea of what space-time looks like at the tiniest possible scale, the Planck scale.
Right. He pictured it as this chaotic, violent soup of geometry, little wormholes and space-time bubbles constantly popping in and out of existence, pure random geometry at the bottom of everything.
But again, if MT is correct, the fundamental ingredient can't be geometry. It has to be motion.
Yeah.
So how does it reinterpret that chaos?
It reframes the foam not as random geometry, but as a sea of short-lived structured motion attempts. At the Planck scale, the universe is constantly trying to form stable, synchronized patterns everywhere at an incredible density.
And most of them just fizzle out.
Almost all of them. They fail immediately and dissolve back into the random thermal background. They don't have the internal stability to reinforce themselves and persist.
So the geometry we see, the stable space-time, is just a description of the tiny fraction of motion patterns that succeeded.
Exactly. The whole question flips. It's no longer what is the geometry of the foam. It becomes what motion patterns are self-reinforcing enough to last. And this moves us from Wheeler's goal of geometrodynamics
to what MT would call motiodynamics,
Ooh.
where geometry is just what stable motion looks like.
It's a radical refounding of the whole project.
So if we pull this all together, motion theory really feels like the next logical step on Wheeler's journey. It keeps his biggest insights, right? Gravity as geometry, black holes as information puzzles, quantum mechanics pointing to an information-based reality.
It validates all of that, but it extends it by giving the abstract bit a physical home in motion. It provides that testable ledger rule, the price of information, and it gives a physical mechanism for the participatory universe through this idea of delayed retuning.
Wheeler famously said, "We are no longer satisfied with insights. We want equations."
And MT points the way to those equations by saying, start with motion. Write down the math that describes how motion patterns synchronize and resist change, and the rest, geometry, gravity, everything, should emerge from that.
The ultimate bet here is on simplicity. The idea that there is one deep, simple story tying it all together.
And that story is this. Everything is motion, structured into patterns that can remember, compute, curve, and ultimately ask questions about themselves.
That idea that we are self-aware patterns of motion questioning our own structure is maybe the ultimate answer to the IT from VIP puzzle, something to think about until our next deep dive.